Okay, now, please, any question?
Can I ask one question?
Sure.
What will happen?
Bring more microphone.
No, that's okay.
What will happen if you switch on the Nicron heater and add 2 or 3 watts?
Known amount of without disturbance.
I don't know. Because now maybe it will be better. But the problem is we have, like Pyrex glass. The limit of temperature of Pyrex glass is about 300 Celsius. Now we stay at 200 inside, 260.
Just by adding 2 watts.
Okay.
See if it goes up by
Okay. We have only one, okay. Taking a problem, only one power supply, okay. Other point, here we are very close to the limit of breaking of the wire. I don't want to get accident. Because some accident happen, really big problems for everybody. Because this one, we ordered special quartz tube in Italy, impossible to find, Europe, so in China. They make special for us, and we pay just symbolic money, only $10. They say, if it works, please add my name in the text. Okay. Wonderful. It arrived in Italy. They make a special with thick wood. For China.
That'll be me, sir.
Stop. Sorry, otherwise continue. Okay, so when I come back, I open the laboratory 25, some progression. I don't know if start with the new reactor or just try to insulate this one, and I want to try, I don't know if it's possible, to get self-sustaining reaction. Because I think it's the most convincing, because the mistake can be everywhere. It seems simple reactor, but really a lot of so skilling and error can be subtle, I don't know explain. So if we have self-sustaining, nobody can say anything. And then,
you can decrease the temperature and decreasing the heater power gradually.
No, now I use, okay, but now I use the way to have very large dissipation. So active length only 10 centimeter. The total is 30 centimeter. I want to dissipate for safety. If something wrong happen, I don't have any possibility. So I make a very large dissipation. But to get self-sustaining, I have to screen, make a reflector and insulation. But not here, because okay. So, but I want to try as soon as possible self-sustaining. So everybody will be convinced that I think it's necessary.
Francesca, when you're conditioning or preparing the wire, you're cycling it around about 600.
More.
Yes?
Okay.
Yeah, can you compare your experiment with the demo in Japan by Aratan and Zhang, and in what sense your system is better than theirs?
Better. My system is different, not better, different. Arata was so clever to think, to realize that the nanomaterial is damaged because of sintering. And he made nano composite with zirconia. So was key point. To be true, we have indication that the sponge effect is good material, but we don't know how to stabilize. We just observe by same, sponge, chest heat. No sponge, no chest heat. Correlation. But we don't know how to do. So by ourselves, we go and partially following the experiment of Iwamura, I don't know if he is aware, he told multi-layer can be good candidate. So we make a simple, we are poor group, not rich like Mitsubishi. We try a multi-layer, means palladium wire is our specialty, and we put about 50 layers of mixed elements. We realize only one element not good because collapse. It will be several different, and we get, I think, very good result for a long time. But maybe we didn't realize very well why. We just observe mistake, no. Right. After a demonstration at the Yokohama conference 2005, oh, now I understood why I was really stupid. All the but one. Okay. So we try to go in this direction. Arata was the first to use palladium, that was the standard zirconium, deuterium. He make calibration, make experiment with deuterium, get some anomalous effect with hydrogen, almost nothing. So it was convincing. Simple, simple experiment is very convincing. Make something very complicated, both error maybe somewhere. After I made even palladium nickel alloy, and it was better than put palladium. So it was really, it went far. But the people complain, oh, why you are the nickel, just walk up. Okay, anyway, he said, these are data, experimental data. I don't know why, but palladium nickel better than palladium. Point. I go on. If you know, don't want to make comments. So, yes.
Francisco, I know the president and founder, one of the co-founders of National Instruments, was instrumental in us being able to demonstrate this experiment here and also in Texas. And I'm wondering, could we have Brian come up and explain? I know for me, I seem to be spending more time trying to get my instrumentation to work than my experiments. And I see a lot of heads going up and down. So Brian, can you come and maybe tell a little bit about the instrumentation system?
Sure.
Brian, by the way, is a National Instruments person who flew here from Texas to help get it set up.
Yeah, thank you. What we have here, we've come up with rather crudely for, like we said, we worked day and night for about a week to get this working properly. We were set up with just a standard, it's a PXI chassis, which is essentially just a holder for what we have as PXI modular instruments. So it's kind of like a PCI bus on your computer, except in an instrumentation form with synchronization and timing. And from there we have our controller module, which has a quad-core processor, just like a laptop computer that runs Windows and LabVIEW, which we programmed the application with. From there, we simply have just a SMU, source measurement unit, that's simply just supplying excitation voltage for our pressure transducer. We're reading that in on one of our standard data acquisition cards. We have an SC Express module, it's called, that has 32 thermocouple measurements on it. Signal conditioning is done here. Low-pass filter with cold junction compensation for temperature measurements. We're up to 32 channels. We currently have 8, including an ambient temperature measurement. And we have 2 digital multimeters, so 7.5-digit multimeters in here. That one is performing a current measurement and one is performing a voltage measurement. So from there we can calculate the total power input, I times V, and also the resistance of each wire with the division. So to make measurements on each wire, there's actually the constant-on wire running through the system, and then a reference wire, which is the nickel chrome wire, and we want to do measurements simultaneously on each of those, or not simultaneously, but close to each other. So we're doing sampling every 10 seconds here, hardware timed, synchronized, and every time we do a current measurement and a voltage measurement on one wire, we have a switch module that will then switch which channel we're doing or which wire, and then taking the same current and voltage measurement on the other channel. And that's the way we're getting, calculating our power input and also the resistance ratios and things like that. The power output is just done through Stefan Boltzmann law, normalized to room temperature with a thermocouple on the external of the glass, so we assume that that's a underestimate of the actual temperature being radiated by this material. And from there, we did a calibration earlier in which we looked at the, basically we wanted to run the system before it was being cleaned. So Dr. Celani suspects that the surface may have been contaminated or there may have been defects or something like that. So what we'd like to do is burn off the excess material and try to get a reference point at which we could calibrate a zero reference. So what we did is essentially turned on the power, waited for the excess power to essentially level off, and slowly adjusted our calibration constant in order to get roughly zero excess power. And that was done for about 40 or 50 minutes beforehand, and that's kind of what we're using our base level. This is the exact same base level, in fact, that was used in Austin, Texas, the same calibration, so we know it's consistent with what we did before. And so once we had that, we shut down the experiment, we turn it on, and that's when we start seeing the excess power compared to this calibration.
To use the Stefan Boltzmann's law, you need to know the temperature of the wire accurately.
No. Okay, sorry. This is, I think, is a very big misunderstanding in the Stefan Boltzmann law. We measure only the radiation outside the chamber. What happened inside, I don't care. Can be gold, can be some nice girl dancing, I don't care. What I need, just the temperature outside. So,
yeah, but that's not uniform.
Underestimating.
No.
Yes, but I don't KV and emit. With Stefan Boltzmann law, with is better. So, it's simplified.
Wouldn't much of the heat simply pass through the glass from the electrode, and so that there would be two distributions outside?
The heat comes of the, okay. In the presentation yesterday, I showed. In the demonstration yesterday, I demonstrate that the source of heat is inside the cell. But the temperature of the cell inside can change, changing the type of gas, vacuum, helium, argon, everything. But because I don't know which one, because maybe some pollution, something, everything can be. So impossible to me to know what is inside. I just measure the temperature outside. Outside is independent from inside. And moreover, something helped me. The thickness of glass is large, 3 millimeters. The conductivity of glass is not so large. So it homogenizes in some way the temperature. So I hope no mistake. It can be another. So if we have some doubt, it's time to ask questions. He helped me.
Okay, fine.
At this temperature, it seems to me that most of the heat is by convection and not by radiation. So why don't you do a calibration at different powers with a resistor?
I make a calibration, 5 watt, 15, 30, 48, and 61. But problem of calibration is another. To calibration is use inert gas. Unfortunately, inert gas or vacuum. With hydrogen impossible. But the same, absorb hydrogen, so give excess energy immediately. You don't watch my document, very bad. So, okay, speaking seriously, the skeleton geometry absorbs everything, really everything. So, but if you make the experiment under hydrogen has the good property to break nanomaterial. If you just use it in gas or vacuum, you have a sintering. So when you make a calibration, you destroy the wire.